Chapter 30. "This just doesn't make sense," said Jason. "What's that, Doctor?" asked Dennis. Dr. Dennis Green was Jason's assistant, and by all rights he was just as qualified as Jason for the work they did on the particle accelerator. Dennis had earned his master's in high-energy physics at UCLA, then earned his doctorate at no less than MIT. He was quite skilled at understanding the emerging fields of quantum physics and how it relates to string theory. In fact, he had given several speeches on the subjects with TED Talks, and his discourses were always sold out. Letting out a guttural groan, Jason uttered what was bugging him. "The numbers keep coming back the same each time. I just don't get it." Once getting that particular sentence out of his system, he then looked at his compatriot askance. "Dennis, when will you ever start calling me Jason?" asked Jason for the millionth time. It was an ongoing joke between them now. "As soon as you ain't a doctor," replied Dennis in his usual cheeky manner. His Texas drawl notwithstanding, Dennis had an affect that was disarming to most until you realized he was one of only a handful of individuals who could actually understand the inner workings of space and time, insofar as man understood it, that is. It was commonly felt that a Nobel Prize was inevitable for him. Rolling his eyes, Jason returned to his work. Dennis thought about how his partner in the lab was equal to his own set of qualifications. Many times the two of them had had long conversations about how Jason's wife, Mickey, didn't actually know what Jason did for a living, much less the extent of Jason's education. Dennis always felt that it was such a juxtaposition that Jason was so dedicated to his work and his research, and at the same time had such a good marriage. Dennis himself had been married before, but his wife just couldn't hack it. It wasn't really her fault, though. Dennis had been so young and yet so dedicated to his education and work that he just didn't give to the marriage all that he should have. He still technically had a good friendship with her, but she said she was just too lonely, and she needed more than what Dennis could give. "So, what is it that doesn't make sense?" asked Dennis. Realizing that he had never explained what precipitated his original outburst, he then replied thoughtfully. "Well, so you know how we've just got the detection chamber to the point now where we are experiencing a high level of accuracy in the collisions?" "Yeah. Are the results coming back differently from what you expected?" asked Dennis. "Well," continued Jason, "I've been analyzing the results and, well, that's just it. They are exactly what I would expect." Scrunching his eyebrows. "Okay. And that's bad," Dennis replied with a quizzical expression on his face. "Well, no," acquiesced Jason, "if you're into doing the same thing every time and expecting different results." "Okay, so what do you have in mind?" asked Dennis. Sitting back in his chair, Jason crossed his arms in front of his chest and reached up to stroke his chin. Dennis had seen this stance on Jason many times, and he knew that when he had this type of look, it was when Jason would come up with some of the most ingenious ideas he had ever heard of. "Studying these results makes me feel like," Jason explained, "like we've been waging a fruitless pursuit of knowledge. Like we're standing on the shoulders of giants, yet never forging new ground. I just have the feeling like there is something right there in front of us, and we're missing it. Like right here on my desk, there is the building blocks of something that nobody has ever worked on before. Like there is something here that is an opportunity to forge new ground into a new area of science." Jason got up from his chair and, almost in his own world, wandered over to the window to his office. The office he currently occupied had all the appointments of luxury that you would expect for someone who was as instrumental in the Super Collider program as he was. Walnut bookshelves occupied the entire west and north walls. The desk was so large Jason sometimes wondered how they even got it into this office. Plush carpet and overstuffed furniture balanced out the hard edges of the woodwork. A floor-to-ceiling window on the east wall, though, looked down from Jason's office into the main science and detection room, which housed, among other things, the Super Collider detection apparatus. This device was housed in a room 60 meters in height and 100 meters in length. On two opposing sides of the room, the particle accelerator entered and exited, and in the middle of the room was the main detector apparatus. It was an amazing sight, really, but right now the grandeur of this man-made marvel, as well as the hundreds of technical minions climbing all over the apparatus as they serviced and maintained the electronics, was lost on Jason. "You know," said Jason while looking out the window, "I'm thinking of something I read recently about Einstein, and how, in his early life, his successes were due to him not having a problem with breaking the rules." "Yep," agreed Dennis. "At that time, there were commonly held understandings of physics and the universe, but the whole reason he was so successful was because he wasn't scared to break the rules. He didn't take things he had been taught as gospel, but instead he asked questions that basically amounted to scientific heresy, or at the very least, something that could amount to occupational suicide. He simply asked, why?" Turning to face Dennis, Jason added, "Exactly. For instance, why was Isaac Newton right? Are we sure he was completely right? Was it possible there was something that Newton wasn't completely right about?" Then, turning back to the window, Jason then added, "That attitude eventually earned him the Nobel Prize, and helped him unlock a lot of secrets of the universe that had been hidden before. He was a rock star of his day." Now, though, Jason was racking his brain with the same conundrum. Why? Why do we do the same experiments and expect something different? "It's almost like," Jason thought out loud, "like we are a person in second place in a race, always trying to catch up to a place that has already been experienced by someone else." Pausing for a moment, he then said, "Maybe we need to stop just detecting. We need to—" Swinging around to face Dennis, he then exclaimed, "That's it!" Dennis looked up at Jason. "What's it?" "We need to stop just detecting. We need to start reacting," said Jason. "Run that past me one more time," said Dennis. Stopping to gather his thoughts and returning to his desk, Jason then proceeded to explain, "You know how all this," gesturing to the scene out the window, "is designed to detect the nature of matter and the nature of the universe in general? How it's based on the pursuit of discovering the building blocks of matter?" "Yeah, Physics 1A, first-year student stuff," observed Dennis. Sitting down in a mock-exasperated manner, "Exactly my point," said Jason while making a magnanimous gesture. "We have been lost in the mire of what really amounts to first-year student stuff, as you put it." Jason made air quotes with his fingers. "But what if, instead of endlessly working to detect the building blocks of matter, what do you say we start creating reactions that will tell us more about what matter is made of?" "Not following you," said Dennis, more intrigued than confused. Looking thoughtfully as he walked to his whiteboard, drawing a basic atom, he continued, "It's simple. Right now, we are taking innumerable numbers of protons and colliding them together. But what would happen if we took different materials and subjected them to the particle streams? What would happen if we did that when creating an environment with different magnetic fields, or different atmospheres, or when using different light wavelengths in the reaction chamber? There are so many possibilities of different environments that we could create, and the possibilities of what we could discover are almost endless." Dennis sat back in his armchair near the couch and considered what Jason had just proposed, as he rested his chin on his closed fist. "Interesting," said Dennis. "The thing of it is, though, undertaking a program of searching for the different reactions like that could easily turn into a fool's errand. It could be like, we use this magnetic field with this gas and this frequency of laser beam, nothing happened. Then documenting we use that magnetic field with that gas and that frequency of laser beam, nothing happened. And so on and so on. It could easily be rather unrewarding. But then again, Dennis added after some thought, it could also be the first rung on an increasingly interesting ladder into an unknown branch of science that nobody's ever seen before. What kind of reactions do you think would happen? Asked Dennis. Well, now that is a good question, replied Jason. I remember one of my old professors always used to say this one phrase that ended up sticking with me. Before starting a new set of experiments, he always said, let's get this started because I don't know what I don't know yet. Then, speaking about creating a reaction chamber, Jason then said, I need to know the questions first before I can find out the answers to them. Really, we're talking about a field of study that hasn't been done before. For instance, Jason continued, we've always personally been interested in the interactions of materials when they are bombarded with steady stream of protons or electrons. Can the atomic state of the material be measured and perhaps isolated? Can the energies inherent in the atomic bonds be counteracted and or reassembled? Will different environmental factors affect this? What will happen when we do this with different materials? Can we finally get to the bottom of the whole wave versus particle question? Atomic bond dissolving and restructuring? Now that's an interesting idea, conceded Dennis. Now stroking his own goatee, Dennis retreated into his own reverie, contemplating what Jason had just proposed. You know, I've been working on some thought experiments lately surrounding that two-slit experiment, but a variation of that centers around the interferometry technology used at ALMA. Oh yeah? Tell me more, inquired Jason. Well, continued Dennis, you know how the radio telescope array at the ALMA location in Chile creates an image based by inferring the observable state of the parts of an image based on the contrast between the observation points, right? Not really following you, replied Jason with a grin. Keep in mind I'm really interested in things that are really small, not so much the really big. No problem. Same here mostly, but astronomy was a pet field of study for me when I was a postgraduate student back in the day. These days, it is more of a hobby than anything else, but as I was kicking back on the couch in my home office the other day, I started thinking about how ALMA creates an image. You see, Dennis got out of his chair and walked to the whiteboard himself and started drawing. There are about 50 or so smaller antennas that are used to create images. Those antennas are designed to receive the radio signals from deep space representing the visible light waves that have shifted so much that they represent radio waves now instead of light. Pointing to the whiteboard, he then said, each of these dots here represent one dish antenna, and each of them is about 20 meters across. They receive the radio signals and then send this information to the supercomputer systems that are on the site. The thing is, though, these individual antennas are physically separated on the Atacama Desert by distances of anywhere from 100 meters up to a distance of perhaps a few thousand meters. As a result, they have the radio frequency image where the antennas are, but nothing in between. Oh, I get it. It's kind of like looking at space through a spaghetti strainer, injected Dennis. Exactly. So the question is, how do they create a complete, cohesive image that doesn't have a lot of voids in it where the antennas aren't? Replied Dennis. Pointing to a random area between two of the antennas drawn on the whiteboard, he continues, in other words, how do we figure out what the image looks like in these areas where they didn't have an antenna? You got me, said Jason. Well, replied Dennis as he replaced the cap on the dry erase marker, the answer is that they use something called interferometry to postulate or infer. Dennis now made his own set of air quotes with his fingers. The image in those non-observed areas. They do this with some pretty sophisticated mathematical calculations and some pretty stout computing power up there. Oh, okay, I understand now, said Jason. They may have these enormous areas that aren't actually observed, but since they do have the data from the areas that actually are observed, then they can basically calculate what things look like in the area between the two antennas, based on the imaging that they do have from those antennas. Exactly, replied Dennis. They take what they do see on any 2 points, and then they calculate what they probably would see between them. Doing this, you end up basically creating a huge virtual radio antenna that is literally many kilometers in size, without having to deal with the natural physical distortion that would happen with a physical structure of the equivalent size. In fact, the ALMA Observatory in Chile has baselines of up to 15 kilometers. Baselines? Not familiar with that term as it applies here. Well, a baseline is the data coming from a pair of antennas at the facility. It is the data from such a pair that is used along with a lot of mathematical calculation, which enables them to observe, or to at least infer, an observation of what is between them. And since you not only have the radio antenna, but you also have the rotation of the Earth, the movement of the Earth around the Sun, and the movement of the Milky Way galaxy and the universe, you can mathematically account for that and, in fact, use it to your advantage to focus on a wider area of the sky. You literally have the ability to see anything you want, even though you don't have an enormous radio antenna, such like what they had at the 188-acre wide dish at Arecibo, Puerto Rico. Okay, I'm following you. But what does that have to do with the two-slit experiment? Asked Jason. Well, continued Dennis, the two-slit experiment showed that particles can sometimes act like particles, but sometimes also act like waves, right? Yes. And it also showed that the act of observing the particles that go through the slits actually end up changing the state of the particles, since the behavior returns them to acting like particles instead of behaving like waves, right? Asked Dennis. Right again. First-year student stuff, replied Jason. Thinking for a moment, Dennis then continued, You ever watch Star Trek? Of course. I'd have to turn in my geek card if I didn't, laughed Jason. Chuckling, Dennis replied, That's for sure. Okay, so you remember how they supposedly made it possible to create a transporter in the series? Yep. They have this thing that they call a Heisenberg compensator, which is a whole lot of fiction. Right. Now, think about this, though, continued Dennis. The thinking behind that compensator is based on Heisenberg's uncertainty principle, which states that you cannot know or measure the position or momentum of a particle without changing the position or momentum of it by the very act of observing it. Now, this is something I do know about, replied Jason. Using an observation device that would, say, send in a light source that is sufficiently tuned to figure out where a particle is, would inherently change the particle to a state that was different than its original position or momentum. For it to be observed, transported, and reintegrated somewhere, you would have to compensate for Heisenberg's uncertainty principle, and somehow observe the position and velocity of the particle without changing it. Otherwise, a person would go into the transporter on one end and come out as biologic soup on the other end. Right, said Dennis. He then raised his index finger and said, But what if you didn't directly observe the particle itself, but rather inferred its position and movement through a variation of that interferometry technology we were just talking about? You would do it by a measuring device that wouldn't directly interact with the particle. If you were able to do it that way, then you would end up knowing the exact position and velocity, and you wouldn't have changed anything about the observed particle. Sitting back in his seat, Jason let all this sink in for a few moments before replying, To do this, you would have to use detection equipment that wouldn't. Suddenly standing up, Jason got very excited. Amanda, he shouted. Jason was referring to the Antarctic Muon and Neutrino Detector Array, also known as AMANDA, located in the Antarctic that allows for the detection and reporting of neutrinos. These detectors are designed to detect the 65 billion neutrinos that have the ability to pass through any matter, including the human body, every second. Dennis's eyes got very wide now, and he started getting very excited. It was always like this when he and Jason started bouncing off of each other. "Brilliant!" shouted Dennis. "Neutrinos would be just the particle that we would need to do the inferred observation. It isn't running anymore, but we've learned enough from that project so that we could build the same type of neutrino detectors here in the lab. And by using such a small particle that doesn't materially change the nature of the matter it passes through, we could infer the state of the matter it has passed through and then know the position and momentum of the particle without altering it at all." "That's right. Thus," said Jason, "this would mean that we would actually have a real-world way of compensating for the Heisenberg uncertainty principle. And by doing that, we could then theoretically know the state of any matter at a given point in time. Knowing that, we could then perfectly recreate the original structure of the matter at another location." "You're actually talking about the ability to create a real Heisenberg compensator," replied Dennis. After letting this float around the room for a while, Jason started getting a wide-eyed look in his eyes. He looked at Dennis, and Dennis had the same look in his eyes. "Transporter," said Jason. As he nods in muted agreement, "Beam me up, Scotty," replied Dennis with an obvious smile on his face. Holy... Hey, fellow Galimarians, this is Dan Adrian, and I just wanted to say thank you for listening to my book. If you can, please click like down below because it really helps me bring these videos to you and lets me know what you like. Also, if you haven't already, please subscribe and click on the bell so that you'll get notified when I release more chapters. If you have any questions about this or any other of my books, or if you want to know more about what it takes to write a novel like this one, please make sure you leave your question in the comments below. Thanks again. I'll see you soon.